Video is actually going to cover angular momentum, which I did not get to yet, and then probably some statics. So if we talk about angular momentum, well, let's talk about this. So first, the right-hand rule for torque. There is a right-hand rule. Torque is R cross F. Again, R is this moment arm. But if you put your thumb along the lines where the radius is, and you put your fingers along the line where the force is, then the palm of your hand will show you the direction of the net torque. It's very similar to ones we've seen already. This is going through cross product. Remember, it's a vector thing, which the product is actually in the third. All right. If you have a non-isolated system, then the change of the angular momentum of a system will equal the net torque on that system. This is very similar to the change of linear momentum is equal to the net force on a system. Here it is. The net torque will equal the change of the angular momentum. Angular momentum, again, is going to be moment of inertia times angular velocity, or R cross P. So it'd be R cross mv, and that R cross v part would give you omega. Then we come here to system of particles. The total external force will equal the total change of angular momentum. So the external force would be here. It would be force of gravity acting on this. We're going to assume this is frictionless, I'm assuming. Yeah. Block slides on a frictionless surface. Oh, there is friction at the pulley, though. But the total change of angular momentum, so change of velocity here, basically. And since this is rotating around a certain point, your actually moment of inertia would be changing as well. I would just work that one with linear variables, which is what they did. For an isolated object, angular momentum is moment of inertia times angular velocity. So a net torque will equal I alpha. We've seen this already, that the net torque will result in a change of angular momentum. But the other way to say that is that net torque is equal to I d omega dt. If you have an isolated system, then the total angular momentum of the system remains constant. And this is the ice skater stuff. They pull their arms in, they decrease their moment of inertia, which means the angular velocity goes up. So let's look at this one. A disc traveling at 3 meters per second strikes a 1 kilogram stick of length 4 meters that is flying on a flat, nearly frictionless ice as shown in the overhead view. The disc strikes the end point at a distance of 2 meters from the stick's center. Assume the collision is elastic and the disc does not deviate from its original line of motion. Find the translational speed of the disc, the translational speed of the stick, and the angular speed of the stick after the collision. The moment of inertia is, and they went ahead and gave it to you. So here, before, your total momentum is this mass times its velocity times this radius, because it's radius times linear momentum. And afterward, you're going to have the smaller linear, like angular momentum of this object. Again, it's going to be mass times this velocity times that radius. And this, I would say, is I omega. Well, how are they doing it? So again, they're saying the total change of momentum of the puck is equal to the change of momentum of the stick. Of the disc is equal to the stick. And so they called the change of momentum here was r mdv plus I omega minus, and this is the final angular momentum of the disk. This term, this I omega, was this MSVS. And so they rearranged it. And again, it's mass times change of velocity times radius, and it's a negative because the disk lost angular momentum and the object picked up angular momentum. And a little more with kinetic energy, total kinetic energy. 1/2 mv squared plus 1/2 mv squared plus 1/2 I omega squared plus 1/2 mv squared, or minus 1/2 mv squared. So a couple different forms of kinetic energy, but still just kinetic energy. Precessional motion, I just want you to be familiar with it. I don't think you'll see it on the AP exam. You should be familiar with all of these. Know that vector product of A cross B is perpendicular, basically, which is where you're getting the sine theta. Torque is R cross F. Angular momentum is R cross P. It's also I omega. And the only thing that will change the momentum of the system is an external force, external torque acting on that system. So if there are no external torques acting on a system, then the total angular momentum remains constant. So that's what we have for angular momentum. And then static equilibrium right here.
I want to show you something.
Wait just a minute. So we've already established that torque is R cross F, and that for something to be in static equilibrium, it must have no external forces and no external torques acting on that object. So when something is in equilibrium here, it's not going to change its rotational motion or change its linear motion. It can be moving. Okay, now let's do this one. Consider an object subject to 3 forces. Choose the correct statement with regard to this situation. 3 forces act on an object. Notice that the lines of action of all 3 forces pass through a common point right here. And so this plus this plus this, well, I can already tell you that if they all pass through a common point, you can put your axis of rotation right there and there's no external torque on it. So it is in torque equilibrium. But since there's a net force going up, and it looks like there's a net force that's probably going over to the right, it is not, object is in torque equilibrium but not force equilibrium. Not yet. Center of gravity, same thing as center of mass, basically. Robin, go away, please, for a minute.
But I want to show you.
I know, I want to look in just a minute. Static equilibrium, again, all the sum of the forces has to equal 0, sum of the torques has to equal 0. Here is seesaw. We did the ladder problem. There's a beam which is held up by a rope, so all the forces are there. I would put my axis here and say some of the torques around that point. Don't do that. And you don't have to know the elastic modulus or the Young's modulus or the bulk modulus, so we're going to skip through those. Don't have to know that. Don't have to know those. You really just need to know static equilibrium here. These are the conditions for static equilibrium. And I'll do one more on uniform circular motion, then oscillations of gravity, and I think that's about it. I'm sorry, it's taking me a little bit.